Okay. Hello students, welcome to the lecture series of M.Sc. Part 1 Physics of the subject Mathematical Methods in Physics. Okay. In the last lecture we discussed about the harmonic functions. Today we are going to discuss these counter integrals. Okay. So let's start. So first I am just give the basic idea of the definite integral. So when we study the definite integral, so suppose this phi is a function of t. We can write phi 1 t plus eta into phi 2 t. Okay, this is a definite integral. So some basic rule of the integrations if we apply here, so we can find this this phi 1 and phi 2 value of this phi 1 and phi 2 if we apply the integration. So like this phi 1 t and this phi 2 t, this is real function. Okay, so by using this basic rule of the integrations, we can calculate this phi value of this functions phi t. Okay, so this is about the definite integrals. This phi is a function of t. Okay, that's a point what I am talking in the complex number. So that's why I am this give the introduction about the definite integral. Okay, so now the in the complex functions, we know that this z, we can write z is equal to x plus eta into y. So here for the counter integral, if this z functions, we know that these z functions, if we represent in the graph, so here two variables x and y. So according to z, if this point is z1, z2, okay, and so on. So this z1 point is vary according to this x and y, because this z is a function of x and y. Okay, so here two variable vary, then this z is vary, and if this z is vary, then function is vary according to the or corresponding to this z1, z2, or so on. Okay, so if I write this z is a function of t, okay, and this x is also a function of t plus eta into y is also function of t. So this z or this entire expressions that depend on the t. Okay, that is t is one parameters. Okay, and if we consider the function, so this function also, if we write the function or integrations for this line, suppose this is z1 here, if this z1 is a function of t, z2 is a function of t, if we integrate this line from this point, suppose this point is z0 to zn, this is a interval limit or the limit. So if we integrations, take the integrations of these functions, that is integration of fz dz or this curve. Okay, this is a curve. So that is integration c fz dz, and this is the expression for if we consider z is a function of the x and y. If we write in the term of this t, here is only t is a variables. Okay, so we can write, okay, this c is equal to integration c f z is a function of t, and this dz we can write, we know that z is, and if we find this derivative, so it is z dash t dt. Okay, so this dz can be rewrite in these terms. Okay, So this is this entire expressions, these ones, that is only depend on this t value. Okay, so this is the parameters or a parametric way to calculate the counter integrations. Okay, so this is one way. So I am not going to discuss this detail of this parametric way. Okay, so let's another aspect to find the value of this curve, so that we are going to discuss. So that is very important. So that aspect is here I am consider one graph. Okay, and this is x and y and one curve. This is a curve I am considering. Okay, this initial point is A, suppose, and last point it is B. Okay, now Z t is equal to, Z is a function of t, this is equal to x of t plus iota into y of t. Okay, so this is Z, and this A, this point is less than, this is an interval. Okay, okay, so this expressions I plot by this graph. Okay, and suppose this t is different value. Suppose I am considering now this x and y vary, then this z is vary. Okay, so at a different x and y value, different z, and corresponding f of z is different. But here we are considering this t is variables. So at this t there is a different value. Okay, so this corresponding t we can write the different points, that is z0, z1, z2, like this. Okay, so if this interval, that is a is less than or equal to t, or t is less than equal to or equal to b, so if write this value for the interval or partitions, if make the partition of this curve, so that is partition from these conditions. If I write like a is equal to t naught is greater than t1 is greater than t2 is greater than t3, and so on. Okay, and also up to the tn, and this is equal to b. Okay, this is a points. Now this corresponding t0, t1, t2, t3 we can write for t0 we can write z0 points. For t1 this t0, this is a value of the t, and t1 this is also value. So corresponding I am write this point, that is z0 on this curve. Okay, and z1 z2 4 like this. Okay, so up to the if tn is equal to zn. Okay, like this. So these are the point that lies on this curve. Okay, and this t0, t1, if this z1, if I take the point like this z1, this initial point, that is z0, this is this ones. Okay, z2, z3, and here zk minus 1, here is zk, and this is zn minus 1, and this is zn. Okay, these are the point that is lies on curve. Okay, so now this f of z, or the f of, I am considering here one arbitrary point first between this two interval, any two intervals. Suppose z0 and z2, these are the this is the interval these ones. Okay, so between this interval I am consider one arbitrary points, that is psi naught. Okay, this is psi naught. Okay, this is psi naught. And similarly, if between this Z2 and Z1 I am considering the another arbitrary point, that is psi 1. Okay, similarly, like if we consider here also zk minus 1 and zk, here is psi k, that is an arbitrary point. So this point is vary according to this t. Okay, so this t, this point is vary according to this t, and corresponding this psi, the functions, these are vary. Okay, so if I write now this for the interval z0, z1 minus z0, there is a one arbitrary point, that is psi naught, and z2 minus z1, there is an arbitrary point, that is psi 1. Okay, similarly, if I write for zk minus 1 to zk is psi k, these are the arbitrary points I am considering between this interval. Okay, successive interval, if you consider, so z0, z1, z2, z3 up to the zk, and this k value is vary from 0, 1 up to the n. Okay, so like this, this is about this curve what we are considering. So now corresponding this arbitrary point, if I consider the functions, that is f of psi k. Okay, because this k is vary from 0 to n, so that's why here is a considering psi k. Okay, so these functions, if I between this first arbitrary interval, if we take this interval and add like this all intervals. Okay, so here you can write in the summation forms, so that is okay, if for the first. Okay, so in all whatever the interval here, so I am taking the one arbitrary points, and along with the arbitrary point there is a quantity, that is z1 minus z0. Okay, so for this first interval, if I write, so this is f of psi naught z1 minus z0. Okay, this is for the first interval. Okay, z0 minus z1. Okay, so z1 minus z0, and between these two arbitrary intervals there is a one arbitrary point, that is psi naught. Okay, so similarly for the second one, that is f of psi 1 z2 minus z1. Okay, so similarly, if we write all this quantity, this is the interval z1 minus z0. Okay, and this is the functions. So if we write the all terms, like, so it is f of psi k zk minus 1. Okay, so this is expressions or summation or all for the arbitrary points or arbitrary point functions corresponding to this arbitrary points. Okay, just adding this functions corresponding to this arbitrary point psi naught, psi 1, and up to the psi k. Okay, now next we can write this in the summation form, that is Sn is equal to summation over k is equal to 0 to n this f of psi k and this zk minus 1. Okay, so this zk minus 1 is equal to del zk. Okay, so we replace these things zk minus k minus v. Okay. So del zk. Okay, so this is summations of these functions or this curve. Okay, this is simply a smooth curve. Okay, now next point is what, if this n goes to the or it continuously increase, then this del zk is 0. Okay, this is limit approach when this n is go to the infinite. Okay, this is so so if I apply the limit here, this del zk is approach to 0 when this n is to infinity, because this interval is continuously decreasing when this n goes to the infinity, and this is interval is what, del zk is equal to this is interval. Okay, so this n is what, numbers of points. Okay, if on this curve numbers of points is increased, this del z is obviously decrease. Okay, so for this I write, or if apply this limit, so it is limit del zk approach to 0 Sn. So this is equal to integration over curve f of z dz. Okay, this is expressions curve c f of z, and this is called this is, I am directly at this expression from here. If I apply take the integrations and apply this limit, so we get this ones. Okay, integration or curve f of z into dz. So this is a this is called counter integral. Okay, or the line integral. So the counter integral or the line integral. Okay, so I hope you got this concept about the counter integral. Okay, now what is procedure to solve this examples? Okay, solve the example. What is procedure if we try to solve the example? So that is for if c f of z is equal to so you can write a, this is interval a to b f of z dz, and this is, we know this f of z is equal to what, u plus iota into v. Okay, so just you can take this a b also interval. I am using the c. Okay, so it's u plus iota into v, and for the dz, that is z is equal to what, x plus iota into y. So if for the dz, if we differentiate, so it is dx plus iota into dy. Okay, so if I simplify, u dx minus if we multiply, so it is v dy, so plus I into integration c this iota is common, so it is u dy plus v dx. Okay, let me check it is right or not. Okay, right. So this is about the f of integration of f of z dz. Okay, this is a way to calculate the or evaluate these functions or okay. So the So let another concept we will discuss, and then we solve the one example, then you can understand. We follow this procedure okay, when we solve the example. Now simply and okay, simply connected region. Okay, so simply connected regions first we discuss, and then the multiple connected region. What is simply connected region and the multiply connected region? So here I am considering one 2D rectangles. Okay, so in this suppose this is x and this is y. Okay, this is origins. So you consider this one regions. This is one region which is defined with the R. Okay, this is the one regions, and in this region, suppose here is a one point, that is P, and if I draw the one curve, closed curve. Okay, this is close tau. Okay, this is a closed curve tau. Now in these regions, if this curve is shrunk to point P without leaving region R. Okay, so then this regions, or this is called simply connected regions. Okay, then this region is called the simply connected region. Okay, so if this curve, that is if it is shrunk to these points without leaving these regions, then we call this is a simply connected regions. Okay, and those who are not or leaving these regions, when it is shrunk to these points, these are the multiply connected region. Okay, so let's that also we discuss. Multiply connected regions. So there is a difference between the simply connected region and the multiply connected region. So here I am considering one regions that is mod z is equal to 2, and another circle, that is radius mod z is equal to 1. Okay, and here one point, that is P. Okay, so region is what? Regions, that is okay, this is the regions. Okay, in this in these conditions, these regions what are the we are considering. Okay, so here P points. Now in these regions, if I draw the curve like this is a curve tau, closed curve. Okay, and if this curve is shrink to this point without leaving region, then we call it is a simply connected region. But here if it is shrink, so it's leaving these regions. Okay, and that's why we called this multiple connected regions. So that is a difference between the simply connected and the multiply connected regions. Okay, so here if we try to shrink this curve, this is a closed curve. Okay, tau, and to the points, then this it can't leave or can't shrink without leaving these regions. Okay, so that's why this is a multiple connected regions. So this is about the simply and the multiple connected regions. So now let's discuss one example. Then okay, so f of z is equal to z square. This is the examples, and I just given you one. Okay, so okay, this is one way. This is x, y, and this is 0, 0. Okay, so this f of z, this is a given function z square. Now here is total 3 paths. This is path 1, path 2, and this is path 3 to approach this point P. Okay, this is a point P. Okay. So here is a total 3 paths that we can approach by the 3 paths also. So now we want to check this f of z, it is depend on this path or independent on this path. Okay, so that is our task. So let's check. F of z is equal to z square. So if this function is analytical, then this independent on this path. Okay, if this is not analytic functions, then it is depend on the 3 paths. Okay, so let's check that z square we can write x square minus y square plus 2i x into y. Okay. And by the definitions we already discussed in the last sections, that is integrations f of z dz, we can write integration c u dx minus v dy plus iota into integrations u dy plus v dx. Okay, this is what we discussed in the last. Okay. So just using these expressions, I am write this from this z square for the f of z. So integrations c z square dz become integrations c x square minus y square plus 2i x into y dx plus iota into dy. Okay, so this expression I am using for the each path. Okay, path 1, path 2, path 3. Okay, so first path 1, for the path 1, if you consider path 1, so here this we can directly this is equation apply in this y is equal to x. Okay, so we can directly approach to point P. Okay, so here y is equal to x, we can write y is equal to x. So if you put this y is equal to x into this expression, so x square minus y square, so this term is cancelled. If x square minus x square is equal to 0. Okay, so it is integration c. This is first term is 0, so here if you put the 2ix into y, so it is I am substitute replace this y with the x, so it is 2ix square and this dx plus I into dy, so I replace this dy with the dx. Okay, so that is dx plus I into dx. Okay, and so integration c 2ix square dx plus 1 into I. Just take out the common from this bracket dx. Okay, and that is 1 plus I. or the iota. So this expressions, if I write integration 2i 1 plus iota integration c, this is a x square dx. Okay, now this if you replace this c with the 0 to 1 for with respect to the x, because this integration is with respect to x, so I am just taking the limit 0 to 1. Okay, so that is integrations 2i 1 plus I, that is x square by x cube by 3 x cube by 3 0 to 1. Okay, so if I put this 1 here, so it is 1 by 3. Okay, and write for your 0 to 1. So it is 2i 1 plus 1 by 3. Okay, this 3 become here. So 2i by 3 into 1 plus I. So if I multiply now I, so this become 2 by 3 I minus 1. Okay, this I into 1 is equal to I, and the I into I is equal to minus 1. So this is a minus 1. So 2 by 3, this is the result for the path 1. Okay, so just write here result for the 2 by 3 at into 1. Okay, so now if we I am trying to this case path 2. Okay, so I am just using the same these expressions. Now this forgot. So integration c f of z dz is equal to integration c x square minus y square plus 2 into xy dx plus iota into dy. Okay, this expression I am using. So for the path 2, now this path 2 is divided into the two parts. First one is it goes from origin to the here x is a constant. Okay, x is equal to 0 for the first part, and then y is a constant. Okay, so this path 2 is divided into the two parts. So just first I am considering that is x is equal to 0 or x is equal to constants. Okay, so if x is equal to 0 and y is equal to 1 for the path 2. Okay, so x is equal to 0 and y is equal to 1. If I put in this expression, so this become integrations x is equal to 0 and y is equal to 1. So this is a limit actually. Okay, y is a variable, this quantity is variable. So I am okay, so this integration with respect to only y for these conditions. Okay, so I am not putting this y is equal to 1. Okay, so just put this x is equal to 0, so that is minus y square, and here this is also 0. This dx derivative of x, this is already 0, so if you take the derivative then 0. 0 means it is not 0, it is a constant. Okay, actually if we consider here value of x is equal to 0, that's why we consider this 0. So this term is constant. Okay, so dx plus I into dy, so this is for the I into dy. So this is equal to, if we take the limit now 0 to 1, sorry, one more expression here, plus. Okay, this is for only this part. Now if we consider for this here y is a constant and x is variable, so y value is equal to 1. Okay, so now if you put in the same for here, if y is equal to 1, so this expression become I'm writing here first integration c minus y square attain to dy. Okay, so plus integration c. Now if for this case, if I consider y is equal to 1, okay, this is a different thing, so don't confuse. So y is equal to 1 for this case, and x is a variable, so x is variable and y is equal to 1, so this is x square minus 1, okay, and plus 2ix y is equal to 1, and the 2ix, and for here now this x is a constant, okay, here x is a y is a constant, okay. So if we take the derivative of this y, then it is equal to 0, so this term is equal to 0, so just here multiply with the dx. Okay, now you observe these two expressions. This is integrations with respect to the y, and this is integration with respect to x. Means what? This integrations here is a one variable, that is x, and here is a one variable, that is y. Okay, now if we take the integrations or limit, so here limit at 0 to 1, because y vary from 0 to 1, and here also x vary from 0 to 1. Okay. So minus y cube by 3 into I plus here x square minus, so if we take, it is x square by x cube by 3 minus x plus 2I x square by 2 0 to 1. Okay. So this will be cancelled. Okay. So if we simplify, so we get the same result. Here this is 0 to 1. Okay, if okay, I am putting the value minus 1 by 3 plus 1 by 3 minus 1 plus 1I. Okay, okay, this is expressions. So if we calculate or simplify, then we get the 2 by 3 into 1 to minus 1. Okay. This same expressions, the same result we get for the path 2. Okay, so this 2 by 3 into I minus 1, this is result for the path 1, and for the path 2, this is result 2 by 3 into I into minus 1. And same if we calculate for the path 3, so here only change is what, this path follow first and then next. Okay, so here y is a constants and x is a variable, and in other terms y is a variable and x is a constant. Okay, so same result if we find this or for the path 3, so we get the same result. So from this total 3 result, if we got the same result from path 1, path 2, path 3, so we can conclude like this, this f of z is analytical functions. Okay, this f of z is equal to z square, this is analytic function, and that is independent of path. Okay, so this f of z is independent of path, then we call this z square is a analytical functions. Okay, so this is we can say if this independent and this is a analytical function. If it is depend on this 3 path, if it is depend, then this path 1 we get a different result, for path 2 we get a different result. Okay, then we can say this f of z square is not analytical functions. Okay, okay, so let's stop here. Thank you.